Good morning and welcome to Marposs. Today we are opening our new leak test webinar series. The session today is a general overview of production leak test methods. I am Gene Grilly, a Marposs technical specialist based in Auburn Hills, Michigan, with our leak testing team. I have over 20 years experience servicing, designing, and selling leak and flow test instrumentation. I have worked with fluid, air, and trace gas leak test systems. So that I stay on track, please save your questions for the end of the presentation when we'll have a short question and answer session. If you need more detailed information or help, please feel to reach out to me after the presentation. As we get started, I'd like to offer a brief introduction to Marposs. One partner, many solutions. Marposs is a leading global supplier of metrology inspection instruments and systems. Marposs started in 1954 in Italy. We have a physical presence in 34 countries with over 80 facilities worldwide, employing over 3,700 people. Marposs provides gauging and inspection systems to many of the key industry segments, such as medical device, pharmaceutical, automotive, aerospace, packaging, consumer appliance, and electronics. As we say, one partner, many solutions. Marposs has three main solution centers for leak testing. The first is Tecna, based in Mirandola, Italy, specializing in leak test instruments. The second is HETEC, or more formally, helium technology. As the name suggests, they specialize in helium and other trace gas systems. They are based near Milan. The third is MG. MG specializes in leak test and assembly systems. They are based in northern Italy. Tecna leak and flow test instruments. Tecna was founded in 1983 in the heart of the Italian biomedical industry. This area has over 100 of the largest global medical device companies with over 5,000 employees and over $1 billion in revenue. Tecna had at its start in industrial process control, specializing in production leak test instruments. Shown are a few of the latest standard Tecna instruments, everything from simple pressure decay, mass flow, and even calibration equipment. Today, in addition to the incredible leak and flow test instruments, Tecna has developed a revolutionary solvent dispenser for outer and inner bonding medical tubes. While Tecna may have gotten its start in the medical industry, we now supply a lot of leak and flow test instruments for automotive, aerospace, consumer electronics, and packaging markets. HETEC was started in 2010 to answer all the requests Marposs was receiving for trace gas systems, particularly what are referenced to as hard vac mass spectrometer systems. These systems require a special sealed chamber and vacuum system to allow the mass spectrometer to operate properly. MG got its start in the metrology world in 1954, specializing in attribute gauges, which led to MG developing automation assembly systems. Today, they provide automated leak test and assembly systems to many of the world's largest automotive customers. They can integrate technical leak test instruments into their solutions, as well as provide trace gas systems similar to HETEC, but specializing in the sniffing and accumulation test methods. One of the things we want to talk about is, what is a leak? When we say leak, we are referring to the actual hole, not the fluid that is passing through that hole. Normally, a leak is the actual defect in the part, whether it is a crack, porosity, or a missing gasket. Leakage, now that's the fluid that is leaking through the hole or leak. When we say fluid, what we're referring to is either a liquid or gas that can flow. Why do we leak test? There are many reasons, but the big three are to prevent a fluid from escaping or entering where it should not, to prevent fire and explosion, to detect unreliable components and those that exceed leakage acceptance standards. Something to consider: everything leaks, to just a matter of what scale we are using to measure. For automotive parts like an engine block or transmission case that contain oil or coolant, we normally see leak rates of less than 10 cc's a minute of air, which will prevent puddles of oil and water from accumulating on your garage floor. Even nuclear waste containers are tested for leakage. While that leakage specification is much tighter than what is seen on medical devices, we know that those containers are eventually going to leak. It's just a matter of how much over what time period. As we start talking about air and trace gas test methods, one of the items I want to show you is a chart that shows a relationship between trace gas leak rates and air leak test rates and bubbles underwater. Trace gas people tend to speak in 10 to the minus something millibar liters per second. Air leak test people tend to talk in centimeters cubed per minute or second. And dunk tank people speak in bubbles. So you can kind of see when we're looking at this, when we're talking about a torque converter or something like that, we're looking at 10 to the minus 3, 10 to the minus 4. It's a retention of liquid is what we're trying to maintain on that. When you start getting into stuff like implantable medical devices, you start seeing the leak rates get a lot tighter in the 10 to the minus 9, 10 to the minus 10 range, okay? Normally when we're talking about simple medical devices like dialysis equipment, tubing and things like that, we're in a much, we actually allow a much larger leak rate than what we would see in something that's implantable. And one of the things you'll see a lot of times on specifications is something we refer to as no leak. And really what that is that a lot of times in specification, it shall not leak. Well, there's an allowable tolerance for air to escape where fluid wouldn't escape. And that's kind of where we put the leak rates at. And that's what we're talking about when we refer to no leak syndrome is that everything leaks. It's just a matter of how much over what time period. Next, we take an overall look at primary leak test methods that Marposs uses. First, we look at the air measurement side. We're looking at pressure decay with gauge and absolute test method, differential pressure decay test method. We have mass flow with two methods, which is flow and leak. And we also have a third method, bubble emission, dunk tanks and soap film. And then we look at the trace gas measurement systems where we start looking at vacuum chambers, sniffer, spraying, bombing test, and accumulation. First method we talk about in air measurement is bubble emission. Bubble emission is probably the oldest leak test method. For submerging, we pressurize a part and put it under water to see what bubbles come out. For sealed packages, we put the part in a tank and charge the tank to a negative pressure, drawing out any gas that is contained in the package. Spraying, or more commonly known as soap solution, is nothing more than pressurizing a part and spraying the joints or suspected leak location with a soap solution. If gas is escaping, it will form bubbles. If you have ever installed a natural gas line for a dryer or stove, you more than likely use this reliable method to make sure that natural gas was not leaking. Part volume, test pressure, leak rate. These are the big variables when we start talking about leak testing. How big is the part? How much air or trace gas will be needed to fill the part? Test pressure, will we use positive pressure or negative pressure? Leak rate, how large of a defect are we looking at? For air decay testing, the larger the part volume, the longer it takes to find the leak. The higher the test pressure, the longer it takes to find the leak. The lower the leak rate, the longer it takes to find the leak. The first method we're going to take a look at is what we refer to as gauge pressure decay. Sometimes you'll hear it referred to as absolute pressure decay. Also vacuum decay, we'll get into that same mix. You can see in the graph the pressure decay leak test is comprised of 3 steps. The first step is the fill. We open the fill valves and pressurize the part. During this step, we are monitoring the entire system for a gross leak. After the fill step, we go into the settle or stabilize step. In the stabilize step, we are letting things settle down and monitor for a gross leak. The next step is the measure step, or sometimes called the leak step. Now that we know we can get the correct fill pressure and we do not have a gross leak we can measure and monitor for a small leak. Basically, we set a 0 point and monitor for a pressure loss. We can then set limits on the pressure change, or we can even convert the pressure change into a flow rate. The second pressure decay method is differential pressure decay. You'll notice in the graph the same 3 steps: fill, settle, and measure. The difference in differential pressure decay is we add a second reference volume circuit that is tested alongside the test part circuit. So we can also add a more sensitive pressure transducer that monitors for a difference between the reference volume and the test part. This allows for faster cycle times on large volumes with smaller leak rates. Normally, I see DP being preferred with European-based leak test companies and absolute pressure decay being preferred by North American companies. It is just the way the 2 markets developed. Europe put the technology into the sensor in the early days, and North America put the technology into the electronics. Today, you'll see most companies have both methods, but it's just a preference for which one they want to use. A lot of times when you're talking pressure decay, it's the same thing, whether you're using differential or gauge or absolute decay. So terminology, a lot of times we'll just call that as pressure decay or pressure drop method. Next, we start getting into air measurement with mass flow. Mass flow is a different technique from both pressure decay methods. It does not convert a pressure change to a flow reading. Instead, the mass flow sensor actually reads the flow across its element and provides a signal with the actual flow value. Mass flow can get a bit confusing when mentioned with leak test, meaning sometimes mass flow is used to verify a minimum or maximum amount of flow, and this is used to check for blockages or occlusions. Sometimes mass flow is used as a leak test similar to pressure decay leak tests. So the first way we look at it with air measurement, this is just on a flow test. It is normally configured with a single step. You'll notice two graphs, one for the test pressure and the other for the mass flow sensor. You know, some of the objectives when we're looking at using mass flow, you get a direct reading of that flow, and it does support large part variations without the requirement for a master part. We start looking at mass flow with a leak rate. Now we get into mass flow as a leak test. You'll notice that the three steps are back. We have our fill, settle, and measure. One of the big differences, the fill valves stand for the duration of the test. The mass flow sensor is measuring the makeup air, and it's important to maintain a consistent test pressure during this step. Getting to our first trace gas system, the one everybody thinks of usually is a vacuum chamber leak test. This is the most common test method. And basically the part is put into a test chamber. The part is pressurized with helium, and a vacuum is drawn on the chamber to try and pull out any helium through the test part. This is normally what we refer to as a hard vac system. A lot of times you'll start hearing people call a mass spec system vacuum system. And this sometimes will get confused a little bit with vacuum decay leak test systems, but they're a big dramatic difference. The vacuum's a lot lower level than what you'll see on a vacuum decay system for mass spectrometer. Next, we get into a spraying test. Spraying test is very similar to the previous system. The biggest difference is that we're gonna draw the vacuum on the test part itself and pressurize the outside of the part with helium. We're trying to pull the helium into the part in this case instead of pushing it out. Next, trace gas method is what we refer to as a sniffing technique. This is a method that we use to turn around and locate where the leak is actually coming from. The part is pressurized with helium, and we turn around and use a special sniffer probe to try and locate that leak. This can get a little cumbersome when you're looking at very big parts and things like that, but it's also very good for finding the actual location of the leak as well as what the quantity of the leak rate is. So when the parts really start getting bigger, one of the things we're starting to see used a lot more often is what we refer to as an accumulation leak test method. And basically we put the part into a chamber. It doesn't need to be as special or critical as the vacuum chambers, but what it is we pressurize the inside of the part, and we look for a leak and let the helium accumulate on the outside of the part. This is usually for larger leak rates. You'll see this used in batteries, cylinder blocks, cylinder heads, things along those lines where the leak rates aren't as tight that you need the hard vac systems for. One of the next trace gas methods is what we refer to as a bombing leak test. The bombing leak test, we're going to turn around and put the part into a chamber, pressurize the part in the chamber with helium. And what we're trying to do is force helium molecules into that small little part. After it's been pressurized for a while, we'll turn around and pull that out and put it into a special vacuum chamber and run a mass spec leak test. At that point, what we're trying to do is pull the helium that we forced into the part back out of the part. So if there's a leak, we'll be able to detect it. And this is referred to as the bombing method. We start looking at the leak test methods, just to give you an overview. One of the big things about soap film and dunk tank, those are really heavily operator influenced. If you're not looking in the right locations, you're not able to turn around and find the leaks, or you're not paying attention to how long did it take the bubble to travel out. Sniffing can also be heavily operator influenced. If you're using a manual station, it's how fast are you moving that probe and that type of thing. Even with robots, if you're using a robot arm to move that sniffing probe, you've still got to make sure you're paying attention to the speed of movement and things like that. When you're talking about soap film, dunk tank, and sniffing methods, those usually will give you a location to turn around and tell you where it's actually leaking at, so you can actually know if you can repair that defect or not. When we start getting into pressure decay, mass flow, and some of the other trace gas methods, they're good at measurement, but not at locating where the actual leak is, okay? Which method should you use? And the answer to that, I know it's kind of wishy-washy, but it depends. And here's some questions to help you decide. One of the things you want to look at is, how is that part used? When we're looking at that part, is it normally pressurized? Is it designed to keep water out? Is it designed to bring water in? How is the part actually used? Does it normally operate under vacuum? So what you want to understand is how does the part work, okay? Are there already part test specifications? A lot of cases, you may have documents that already say, hey, this is how you're going to test that part. Are you trying to keep a fluid or a gas in or out of the part? What is the part material? Some part materials, if you're dealing with cast aluminum, are definitely going to operate differently than some of the polys, where they'll expand like a balloon if you pressurize them both to 20 psi. How big is the test part? Some parts just don't lend themselves to testing with air. Large volume parts, like gas tanks and things like that, while the test specifications are valid for air decay leak testing, the cycle time and the part volume just aren't realistic on that. So what you'll see a lot of times is the parts are used with trace gas, and they'll turn on either sniff or use an accumulation method with something along those lines. How many part models and types? Some of the things when you're looking at is part models is normally on pressure decay, and whether it's differential or absolute pressure decay, you need to have a master part, a reference part that you set up to. If you have a lot of various part models, you would have to have a master part for each one of those. One of the things we can do with mass flow is we can set the programs up to accommodate for slight variations in part volume and things like that. It just affects the cycle time. How much risk is there if a part leaks? Some people don't leak test because there's really not a risk to them if the part were to leak or have damage to it. Not all parts need to be leak tested. Things that the FDA pays attention to, things that the federal government pays attention to, like with fuel components and brake components, those all are leak tested. A lot of times those are referred to as inverted delta items. So you track all the data birth histories on those type of leak rates. What are the environmental conditions where the part will be tested? Some places you may have it where it's very cool in the morning, and by early evening it's very warm and hot. So the part temperature changes quite a bit, and that can influence how the part is leak tested. How much time is available to perform a leak test? Sometimes we'll use differential pressure to speed up some cycle times. Sometimes differential isn't a big enough time saver. You might need multiple stations. Is the part tested at multiple stages in the assembly process? This is something we see a lot in the automotive industry, is where castings are checked early in the foundry process, and then early in the machining phases, then all the way on up through the assembly process. They've got different leak test specifications as it moves along in the process. So what you'll see is more of a stack up on the actual leak rate at the end. So in engine assembly, you're looking for the gasket leaks and things like that. You're not looking for porosity leaks that should have been caught back in the machining process. What kind of budget do you have for new equipment, maintenance, recurring operations, and training? Mass spectrometer systems can get very expensive. The cost of gas can get expensive. What type of test equipment does your facility currently use? If your technicians are all very used to using mass flow, it may be difficult to introduce them to pressure decay or some of the other systems. Some of the things that you want to look at is, what type of data collection analysis do you plan to use? You know, if you're looking at a lot of data collection and things like that, you want to analyze it, and you may want to make sure that linearity is an important factor. There are test methods out there that'll give you a go, no-go very accurately, but aren't very linear. So you want to pay attention to that if you're planning to collect data. You know, general rules of thumb on this: air leak test instruments have a much lower operation cost than trace gas. Gauge, differential, and mass flow will equally give the proper test results when set up properly. I see a lot of argument on this, and depending on which company you're talking to, some will tell you that pressure decay is the only way to go. Others will tell you it's differential, and mass flow will definitely factor into that equation. All three, when set up properly, will give you the same result. So if you've got a specification of 5 cc's a minute at 3 bar test pressure, all three systems, if set up correctly, will give you the same answer and repeat properly. Okay. Different situations will make each one better than the other. It just depends on the environment. Most American companies lean towards gauge decay. Most European lean towards differential decay. Mass flow is kind of a newer animal. It's really been out for the last probably 10 years, 15 years. And believe it or not, that's kind of new for this industry. Delta P pressure change leak test systems all use a formula to convert delta P to a flow rate. There's all some type of algorithm to turn on and convert that pressure drop and change into the actual flow rate. Differential and mass flow instruments cost a little more due to the second sensors and additional components. Master parts and seal leak test are normally required. And this is master parts, you use that to turn on and set your baseline for production. This is what you want all your parts to look like. And seal leak tests are there to turn on and help you troubleshoot and set up your systems initially to make sure you got the system set up and operating properly. You know, when we start looking at some factors and variables, the big three we see are clean, dry, and ambient. The parts have to be clean. If they're dirty in that, you've got a potential for masking leakage. Wet parts are the same thing. You've got the potential for masking holes, porosity, things along that line, or being in the wrong spot. I participated in a study with General Motors a few years back where they actually took cylinder blocks and poured a tablespoon of water into the engine block water cavity. And we were actually able to make 200 cc a minute leaks and knock them down to about 8 to 9 cc's per minute, which would have passed their criteria if they were wet parts. But the problem is when the parts dried, they were now leaking oil. So we found that it was really to our benefit to have dry parts when they were doing the leak test. The other thing that plays a big factor is ambient. I know this isn't always easily attained in that type of thing, but pressure decay and differential systems, because we teach them that pressure change, they really want to know that the temperature is consistent. There's methods out there for temperature compensation and things like that that can correct it, but the easiest way to do it is have the parts be presented to the leak tester at a consistent temperature and you'll get consistent readings. You know, some of the best practices we want to look at, make sure the testing method matches the application. You know, there's some places where you're using large leak rates and differential just doesn't work for it, okay? Minimize part volume. Use volume reducing plugs when needed. They can speed your testing cycle. Laws of physics are not changed because of a bad process. Plan for common wall issues. You know, you've got to look and see as if you've got two cavities that are side by side, pressurizing them both to the same pressure means you'll miss catching the leak between the two cavities. So you got to make sure that they're checked sequentially or offset their pressures enough so that you can catch the common wall leakage. Test parts early to ensure cycle time requirements. One of the things we really recommend is if you guys are looking at building new equipment or putting in a new line is as early in the process is let's test some sample parts and verify what the cycle time is going to be. We've got formulas we can calculate out what the estimate should be and what cycle time should be, but there's no substitute for actually testing the parts early and performing repeatability studies just to make sure we got the right cycle time so we can let you know, do you need 1 station or do you need 15? Limit temperature swings, both environmental and part. You know, they both play a factor on repeatability. Design your seals and leak test fixtures to prevent leakage and volume changes. Keep your leak tester, seals, and pneumatic parts accessible for easy maintenance. Design seals and fixtures to ensure adequate clamping and sealing forces for testing. Provide the minimum recommended available air supply, pressure and flow to seal and pressurize the part during leak testing. And you definitely want to challenge your system every shift. What this is you put in your master part and you verify that you get your leak rate, you get your non-leak, your 0, and then you turn on and install your leak master and you verify that it rejects that part of the leak rates. This way it lets you know that the system's capable of doing what it's expected to do. And we recommend doing that at least once per shift. Okay, and with that, we'll turn on and that concludes it for today. but we'll go ahead and open it up for any questions you have, and we can answer those for you. And remember, this is just the first part in our series. We'll turn around and start getting into a lot more in depth on the instruments, different techniques and stuff like that for the individual things as we go along. We'll start tailoring it for some of the more complex applications and things like that. But if you have any questions, feel free to go ahead and let me know.
Hey, Gene.
Yes.
What are the difference? What is a crack and burst test?
When you're looking at a crack test and a burst, those are events that happen. So a lot of times what you'll see is something like a blood bag or a urology bag. You want to make sure those things don't leak, but also you want to make sure they're not going to burst on you with a little bit of pressure. So what we turn around and do is we pressurize that part. And what we look at is at what pressure does the part actually burst. Burst is actually a failure of that component. It is a destructive test. Crack test is a lot of time used, it's very similar to the burst, but it just allows you to know something open. It may be used on a check valve or something like that, where you want to know at a specific pressure that it were to open up and relieve, okay? So we just pressurize the part, and at the crack, it turns around, pops, and we record the event at what pressure we saw a dramatic change.
Thank you.
Mm-hmm. All right.
I guess one more question I have, Gene, if you could just go over the differences between the Marposs Heat-Tech, the Marposs MG, and the Marposs Tecna. I was a little confused by that.
Okay. If you look at Tecna, Tecna really specializes in the leak test instruments. They do the instruments themselves, not the sealing devices. It's the instruments. They build the pressure decay, mass flow, and those type of systems. When you get into Heat-Tech, what Heat-Tech specializes in is the mass spectrometer systems. They don't deal with pressure decay or mass flow. They're always with a mass spectrometer and the vacuum systems, usually with a vacuum chamber. Okay, and that's really their specialty, is the vacuum chambers. When you get into MG, MG is kind of a mixture between the two. They'll actually integrate Tecna and Heat-Tech systems into their assembly systems and their test lines. So you'll have them doing the full automation for leak test, but they also do some assembly stuff like flare work and things like that. So that's really the three differences, but they work hand in hand.
Thank you.
Mm-hmm. And again, feel free to contact me if you have any questions or I didn't answer something you think I should have. But we'll go ahead and we'll conclude that for today. Thank you for attending. Appreciate your time.